Welcome. In this video, I'm going to be going through the multiple choice questions from the June 2019 Physics Regents. Question 1. Which pair of quantities represent scalar quantities? Okay. Remember, scalar quantities are quantities that have magnitude but don't have direction. Displacement, that has direction. Remember, things that have direction are called vectors. Displacement is one, and so is velocity. Once I go and eliminate answer choice 1, 2, and 3, for that reason, what I'm left with is just answer choice 4. Remember, scalars are allowed to be negative, they just can't have direction. So the answer to question 1 is 4. Question 2. A sailboat on a lake sails 40 meters north and then sails 40 meters due south. Compared to its starting position, the new position of the sailboat is. Let's go ahead and draw a picture. So if we're starting at this location and going 40 north and then 40 east, the comparison of the final position to the starting position would be this line here, this diagonal. And I'm going to use, again, a little bit of process of elimination here. It's not answer choice 1, and it's not answer choice 2, because we are the hypotenuse of a triangle, which has to be greater than 40. I also know that the direction has got to be northeast. Okay. And then for selecting between 3 and 4, if I went 40 and then 40 in the same direction, that's how I could end up 80 meters from where I started. But because of the diagonalness, I know that the answer is going to be less than 40. The correct answer to question 2 is 3. I could do the exact calculation by using Pythagorean theorem. So I could take the square root of 40 squared plus 40 squared, and that would give me 57. Question 3. A ball is thrown straight upward from the surface of the earth. Which statement best describes the ball's velocity and acceleration at the top of its flight? When an object moves upwards and right before it comes back down, what we know at the very top of the motion is that the velocity equals 0. If you were to make a graph, it would look something like this. At that point, the object is stopped and is about to change direction. And so what we know is that we have to look for questions where the velocity is 0. Okay, so I can eliminate answer choice 3 and answer choice 4 because they're saying that the velocity is non-zero. The other thing we know about acceleration near the surface of the Earth is that it is always a constant. The acceleration equals 9.81 meters per second squared, always pointed down towards the Earth. So it is in fact not 0. It is a non-zero number, which allows me to eliminate answer choice 1, and the correct answer is 2. Question 4. As a student runs a plastic comb through her hair, the comb acquires a negative electric charge. This charge results from the transfer of. So again, let's be clear. We have got the comb and we have got the hair. And for the comb to become negatively charged, that means electrons have to go from the hair to the comb. Right? The electrons carry negative charge. The hair will be left positive, the comb will be left negative. So first, we can eliminate answer choice 1 and 2 because it is not the protons that do the moving. And then, again, because the comb is acquiring the negative charge, the electrons must be going from the hair to the comb. Correct answer choice 4. Question 5. How would the mass and weight of an object on the moon compared to the mass and weight of the same object on the Earth? Well, one thing we know is that mass and weight measure different things. Mass is a measure of all of the matter that an object has, and weight has to do with the measure of the force of gravity. And we know that gravity on the moon is weaker than gravity on the Earth. So we can eliminate answer choice 4 because we know that those things won't be the same. Now, because mass is the measure of the amount of matter something has, and going from the Earth to the moon doesn't affect that, we do know that the mass is going to be the same. And so what we're left with there is, well, question 1 says that they would both be less, so it can't be 1. And option 3 says the mass would be less. So again, it can't be that. So again, using process of elimination, we get ourselves to question choice 2. All right, question 6. An object is moving with constant speed in a circular path. The object's centripetal acceleration remains constant in. So let's draw a picture. Here's our object traveling in a circle. The centripetal acceleration points towards the center of the circle, which means when that object has changed its position, the direction of the centripetal acceleration has changed. It's still pointing towards the center, but that center is no longer in the same direction. For the magnitude of the centripetal acceleration is given by the speed squared divided by the radius. So as long as it's a circular path, the radius is the same, and the speed is constant, then the magnitude will remain a constant, but not the direction. So that crosses out answer choice 2 and 3 regarding the direction. And then we do know that the magnitude is a constant, so the correct answer is answer choice 1. Question 7. As shown in the diagram below, a rope attached to a 500 kilogram crate is used to exert a force of 45 newtons at an angle of 65 degrees above the horizontal. The horizontal component of the force acting on the crate is. So in order to figure this out, we're going to draw ourselves our triangle here with our angle labeled and the 45 newtons being the hypotenuse of this right triangle. Now, we want to figure out the horizontal component, which means we are looking for sort of the x component here, which if we look at our trig ratios, and we can refer to the reference table on page number 5, we see that we need to use the cosine of the angle is going to be the component we're looking for divided by the hypotenuse. I can also do a little bit of a process of elimination here. The components of a force cannot be greater than the magnitude of the force itself. So I can eliminate answer choice 3 and 4. Those are distractor choices connected to the 500 kilogram number from the question. I also expect at 65 degrees, I expect the horizontal component to be less than the vertical component. In a sense, I could eliminate answer choice. I could eliminate answer choice 2, or I can also, get out my calculator and do 45 times the cosine of 65 degrees, and I will get answer choice 1. All right, question 8. Question 8 states a spring with a spring constant of 68 newtons per meter hangs from a ceiling. When a 12 Newton downward force is applied to the free end of the spring stretches a total distance of. All right, this is a question that has to do with springs, spring constants, and the spring force. We can get the equation for this on page 6 of the reference table. What we find is that the force of the spring equals the spring constant times the elongation length or compression length or the change in length of the spring. And so I've got that the downward force is 12 newtons. I've got that the spring constant is 68 newtons per meter. And then I'm solving for the change in length of the spring. And so the change in length of the spring is going to be 12 newtons divided by 68 newtons per meter. Again, I can do a little bit of process of elimination here, right? It's not going to be answer choice 4 or 3. I'm looking for something less than 1. And again, I can now go over to my calculator and do 12 divided by 68. and I'm going to get 0.1764 continued, which they're rounding to the 0.18. All right, question 9. As a student walks downhill at constant speed, his gravitational potential energy, and then we're kind of like completing the sentence here. So first off, let's talk about the gravitational potential energy. Remember, that is equal to your mass times the acceleration due to gravity times your change in height. So if you're walking downhill, your change in height is decreasing, which means your gravitational potential energy is also decreasing, which means I can eliminate answer choice 1 and answer choice 2. With my kinetic energy is 1/2 mv squared. Both of these equations are on page 6 of the reference table. Well, if v is a constant, then what can you say about the kinetic energy? Well, I can say that the kinetic energy is a constant. Okay, and so the gravitational potential energy decreases and the kinetic energy remains the same. Question 9, answer choice 4. All right, question 10. When 150 joules of work is done on a system by an external force of 15 newtons in 20 seconds, the total energy of that system increases by. And so we want to remind ourselves that the change in energy of a system equals the work done on that system. They're telling us that the work done is 150 joules, which means that the change in energy of the system is going to be plus 150 joules. We don't have to do any extra calculation here. The tricky thing they did do is they rewrote the 150 joules in scientific notation. 150 in scientific notation would be 1.5 times 10 to the second. The correct answer is answer choice 1. Question 11. A person on a ledge throws a ball vertically downward, striking the ground below the ledge with 200 joules of kinetic energy. So we have our ledge. The person is throwing at some speed, some v, that they're throwing downwards. And when it reaches the bottom, they find that the kinetic energy is 200 joules. The person then throws an identical ball vertically upwards at the same initial speed from the same point. What is the kinetic energy of the second ball when it hits the ground? Well, remember, when we're talking about conservation of energy, kinetic energy is always a positive number. It doesn't matter that the ball is going upwards or that the ball is going downwards. The ledge is the same and the mass is the same, so the change in potential is the same for both of them. And so even though the first ball will reach the bottom faster, right, versus the path that the second situation takes where it goes up and comes back down, because they start with the same initial energy, they travel the same distance, so they're going to have the same change in potential energy, and so therefore they will have the same final kinetic energy. Answer choice 1. All right, question 12. 2 construction cranes are used to lift identical 1,200 kilogram loads of bricks the same vertical distance. The first crane lifts the bricks in 20 seconds, and the second crane lifts the bricks in 40 seconds. Compared to the power developed by the first crane, the power developed by the second crane is. On page 6 of the reference tables, we can remind ourselves that the power is equal to the work done divided by the amount of time it takes in order to do that work. And so if we double the amount of time, we will develop half the amount of power, right? If you take twice as long to do something, you need half as much power in order to do it. Question 13. An ionized calcium ion has a charge of plus 2 elementary charges. If this ion is accelerated through a potential difference of 2 times 10 to the 3 volts, the ion's change in kinetic energy will be. So the change in kinetic energy is going to be equal to the electric potential energy change of the ionized calcium atom. That's equal to the charge times the change in potential. The charge here is plus 2 elementary charges times a potential difference of 2 times 10 to the 3 volts. Well, this specialized unit of electron volts is what you get when you multiply elementary charge times volts. And so we're going to get 4 times 10 to the 3 electron volts. Answer choice 4. All right. Question 14. A total charge of 100 coulombs flows past a fixed point in a circuit every 500 seconds. What is the current at this point in the circuit? The current is defined as the amount of charge that flows by divided by the amount of time it takes that charge to flow. Here we have 100 coulombs flowing past every 500 seconds, which is 0.2 amps, which they have decided to add some additional significant digits. It is answer choice 1. All right, question 15. An aluminum wire of length 1 meter has a resistance of 9 times 10 to the negative 3 ohms. If the wire were cut into 2 equal lengths, each length would have a resistance of. This is a proportional reasoning question, and you can also apply some logic here, right? If the total resistance is just equal to those 2 wires added together, then if we cut them in half, they should each end up with sort of half of the original resistance. And so it is answer choice 2. You could apply a formula in the reference table on page 4, where you calculate the resistance based off of the resistivity, length, and cross-sectional area. But really, this is a question that's all about proportional reasoning. Much easier this way. All right, question 16. In an operating electrical circuit, the source of potential difference could be A. Well, a voltmeter and an ammeter are ways to measure potential difference in current respectively. They are meters, they are not sources. If we're then comparing batteries and resistors, resistors don't provide a source of potential difference. There are potential drops across resistors that result in a transformation of energy. You could get light, you could get heat, you could get motion, you could get sound, but you're not going to get potential difference. It is a potential drop, which leaves us with answer choice 2, a battery. All right, question 17. A light bulb with a resistance of 2.9 ohms is operated using a 1.5 volt battery. At what rate is electrical energy transformed into the light bulb? We are looking for the power developed. The power developed, we can get that formula on page 4. We see we're given resistance and current, and so we want to use the version of the formula V squared divided by R. We could complete an intermediate step and calculate the current. And if we calculate the current using potential difference divided by the resistance, we could also figure out the power by then multiplying that potential difference in the current. However, this version of the formula is a shortcut that combines these two. So I'd plug in my numbers of 1.5 squared divided by 2.9. And I'll go over to my calculator and type that in. 1.5 squared divided by 2.9. And I get 0.77586, which they rounded to 0.78. All right, question 18. A 40 kilogram child exerts a 100 Newton force on a 50 kilogram object. The magnitude of the force that the object exerts on the child is. So notice here how we've got our a force pair here. We're talking about the child and the box or object. And so we're told that the child pushes on the box, exerts a force of 100 newtons. And so this would be the force of the child on the object. And then they want us to say something about the force of the object, sort of applying a force on the child. Well, this is a Newton's third law question, which states that these forces are equal in magnitude and opposite in direction. And so the answer choice here is 3. No calculation needed. All right, question number 19. 2 identical stationary bar magnets are arranged as shown in the diagram below. What is the direction of the magnetic field at point P? Well, we remember that the magnetic field around a bar magnet is that the magnetic field comes out of the North Pole, loops around, and comes back into the South Pole. So if we're looking at sort of this axis of symmetry, this line right down the middle, we'd expect the magnetic field from the top magnet to be to the left, and then this bottom magnet to be down. And this is kind of like the question that we were having, question number 2, I believe, right, where we're trying to figure out like the displacement from beginning to end. So in order to add these vectors, I would line them up tip to tail, and then I would draw my resulting vector from the tail of the first to the tip of the last, which leaves me with answer choice 3. All right, question 20. A student claps his hand once to produce a loud sound that travels through the air. This sound wave is classified as. So first off, we know that sound is a longitudinal wave. So I can eliminate 3 and 4. And because it is a wave that travels through matter that is disturbing the matter, that's the matter itself is what's wiggling, that makes it a mechanical wave. And so question 20, the answer is 1. Question 21. A student generates water waves in a pool of water. In order to increase the energy carried by the wave, the student should generate waves with A. And the more correct answer here is answer choice 1. However, the physics Regents folks did decide that an answer of 2 would also be acceptable. Turns out what an answer of 2 changes, it's not the energy itself, it's like the power of the wave would increase at a higher frequency of the same amplitude. So they gave credit for both answer choice 1 and for answer choice 2. All right, question 22. A wave generator produces straight parallel wave fronts in a shallow tank of uniform depth water. As the frequency of the vibration increases, which characteristic of the wave will always decrease? When we see a question like this, connecting sort of frequency to a property that has like an inverse relationship, what we want to remember is that the speed of a wave is equal to the frequency times the wavelength. And those two are inextricably linked. So if frequency is going to increase, the wavelength is going to decrease, always. And so the answer choice here is the wavelength. There are circumstances under which the frequency changing could have effects on these other things, but that is medium dependent. But the one that will always have this characteristic change would be the wavelength based off of the frequency. All right, question 23. A space probe produces a radio signal pulse. If that pulse reaches Earth in 12.3 seconds after it is emitted by the probe, what is the distance from the probe to the Earth? So first off, we know that this radio signal is traveling at a particular speed, and so the distance traveled is going to be equal to that speed times how much time it's traveling for. So then the thing that we have to figure out is, well, how fast is a radio signal traveling at? Well, radio signals are light, so they travel at 3 times 10 to the 8 meters per second. That number, that speed of light in a vacuum, is available for you on the reference table on the first page. It is the third number down. So I just have to multiply that 3 times 10 to the 8 times the 12.3 seconds. And in this example, I'm not even going to really use a calculator. I know, sort of 12 times 3, well, that'll be like 36. And so my answer choice here is going to be 4. Where they're getting these two answers from, 1 and 2, is instead of using the speed of light, they're using the speed of sound. So even though radio carries sound information potentially, it does not travel at the speed of sound. It travels at the speed of light. All right, question number 24. The diagram below represents a light ray reflecting from a plane mirror. The angle of reflection is, remember, all angles in optics are measured from the normal line, the line that is perpendicular to the surface of the mirror or the interface between the two materials. So the angle of incidence here is 70 degrees, and the law of reflection says the angle in equals the angle out. And so the reflected angle would be considered to be 70 degrees. All right, question 25. A light wave travels from one medium into a second medium with a greater index of refraction. Which characteristic of the wave cannot change as the wave enters the second medium? So the only characteristic of a wave that cannot change as the wave enters the second medium, independent of if the wave got faster or slower, if it bent or not, is the frequency. The frequency remains the same when a light wave travels from one medium to another. It's like its signature. It's what makes the light that it is, even though these other three things are able to change. The frequency must remain the same. Kind of like if you were shaking someone's hand, your two hands must be going up and down at the same frequency. Otherwise, you would not be shaking hands. All right, question 26. The speed of light in glycerol is. A hint in understanding this question is the inclusion of the frequency of the light. That's a number you've seen before on page 2 of the reference table. The absolute indices of refraction. The absolute index of refraction of glycerol is 1.47. Remember, the index of refraction, that equation relationship being on page number 5 of the reference table, states that the index of refraction is the speed of light in a vacuum divided by the speed of light in that medium. In other words, as the index of refraction gets higher and higher, the speed of the wave gets slower and slower. And so to figure out this index of the speed of the wave, what I'm going to do is I'm going to take the speed of the wave in a vacuum, 3 times 10 to the 8 meters per second, and I'm going to divide it by the index of refraction in that material. 1.47 is pretty close to 1.5. 3 divided by 1.5 would be 2. And so that can let me calculate that the answer is 2.04 times 10 to the 8 meters per second without necessarily having to take out my calculator, although, of course, you would be welcome to. Answer choice 3 I can eliminate. That's way too slow, right? I wouldn't expect the exponent to change, right, from 10 to the 8 to 10 to the 6. Answer choice 3 is just the speed of the wave in a vacuum. We know it's got to slow down in glycerol, so it can't be that. And it can't be answer choice 4. The light wouldn't travel faster. All right, question number 27. The diagram below represents a standing wave produced in a string by a vibrating wave generator. The question is, how many antinodes are shown in this standing wave? Well, the way I like to remember this is that the nodes are the points at the very ends of a standing wave on a string. And they are the locations where the wave is always at 0 displacement. The antinodes are the places sort of halfway between them where the wave will undergo a maximum change in displacement. The tricky thing to remember is that the antinode is like a location in space, and that string is wiggling back and forth. So this wave would have 3 antinodes, not 6, right? We wouldn't count either side here. What we're counting is sort of the location in space. So the answer choice is 3 antinodes. All right. Question number 28. The Doppler effect is best described as. This is a definition type question. And a question like this, I think the best way to answer is to just read through all of the choices and see if you can identify what is that thing being described. So answer choice 1, bending of waves as they travel past obstacles or through openings. That is diffraction. So we can eliminate answer choice 1. Answer choice 2, change in speed of a wave as the wave moves from one medium to another. That's this idea from the earlier question, right, about index of refraction. It's the speed of light in a vacuum divided by the speed of light in the material. That is not the Doppler effect. Answer choice 3, creation of a standing wave from 2 waves traveling in opposite directions in the same medium. This is describing interference. Specifically, interference that arises and creates a standing wave. So it's not answer choice 3. So at this point, we know it's answer choice 4, but let's read the description. It's the shift in the observed frequency and wavelength of a wave caused by the relative motion between the wave source and observer, again, having to do with frequency. That is the Doppler effect. All right, next, we've got question 29. Which diagram represents diffraction of a wave front as they encounter an obstacle? So again, when we're talking about diffraction, we are not talking about bouncing off of things. So we can eliminate answer choice 3, and we can eliminate answer choice 4. Another important characteristic of diffraction is that the light with the wave fronts will sort of bend and curve. And so you can see in answer choice 1, those waves are curving. And eventually, if you go far away from the obstacle, it'll be like the obstacle wasn't really there at all. Whereas in example choice 2, you see that sort of the wave fronts are chopped off and don't do any bending. So the answer is 1. All right, next. Which types of forces exist between the 2 protons in a helium nucleus? So first, we know that there will be an electrostatic force because protons are charged. And because they have identical charge, we expect that force to be repulsive. And so we can eliminate answer choice 3 and answer choice 4. We also know that the gravitational force between 2 objects with mass is always attractive. It's always attractive. And so we can eliminate answer choice 1 because it's describing a repulsive gravitational force, and it is always an attractive one. And so the answer is answer choice 2, right? So it is the strong nuclear force that keeps those protons in the helium nucleus from moving apart from each other and creating an unstable nucleus. All right, question 31. A meson could be composed of. So to remind ourselves sort of the ingredients and the rules governing the classification of matter, you can go to the charts on the bottom of page 3. So mesons are an example of hadrons. Right? Mesons are an example of that. And mesons are made up of a quark and an antiquark. So first, answer choice 1, a top quark and a bottom quark. Well, those are both quarks that a meson could not be made of them. Remember, the reason for that is if you added up the charge of a top quark and a bottom quark, in this specific example, you are going to get a charge of a third, and the charge cannot be a third for a particle. Next up, we have an electron and an anti-electron. Well, those are not hadrons or mesons. Those are examples of leptons. Okay, so you couldn't do that. We also know that an electron and an anti-electron, those are antimatters. So if you were to put them near each other, they would not last for a very long time. Answer choice 3, a strange quark and an anti-charm quark. Well, that meets our ingredient definition. So a meson could be made up of these. We'll look at question number 4 just for completeness. An up quark and a muon. Well, we're mixing together here quarks and leptons, and so it could not be that combination. All right, question 32. An electron in an excited mercury atom is in energy level G. What is the minimum energy required to ionize this atom? Ionization requires getting to 0.0 electron volts of energy, because past that, the electron will have positive energy and is no longer bound to the atom. If we go to the top of page 3 in the reference table, we can see the energy level diagram for mercury. Reading it for G is a little, for mercury is a little tricky, so just follow those lines carefully. And the energy associated with level G is negative 2.48 electron volts. And so the minimum energy would be positive 2.48. It is true that if you had a photon with 7.9 electron volts, it would ionize the electron in that energy level G, but it is not the minimum energy. 1 and 2 are not enough energy to ionize. All right, question 33. A student is standing in an elevator that travels from the first floor to the 10th floor. So we are in an elevator that is traveling upwards. The student exerts the greatest force on the floor of the elevator when the elevator is. So if the elevator is, if the student is not accelerating, the force of the student pushing down on the elevator is equal to their mass times gravity. If the elevator is accelerating upwards, then the force exerted is going to be the mass of the student times the acceleration due to gravity plus whatever that acceleration is. If, however, the acceleration is downwards, then that force exerted is going to be the acceleration due to gravity minus what that acceleration is. Right? And you can kind of remind yourself of this as well. What if the acceleration downwards was equal to the acceleration due to gravity? Well, then you're in free fall and there would be no force at all. And so let's run through these. Let's go from the bottom up. So first, at rest on the first floor. Well, if you're at rest on the first floor, then you're not accelerating. And so that would not be a situation where you would exert the greatest force. You would have that mg going on. Likewise, if you're moving upward at constant speed, you are also not accelerating. So that could not be the greatest. For choice 2, we're slowing down as it approaches the 10th floor. That corresponds to an acceleration pointing downwards. Remember, to slow down, your speed and your acceleration needs to be in opposite directions. And so this would be a smaller force than if you were just at rest or moving at a constant speed, which leaves us with answer choice 1, accelerating upwards as it leaves the first floor. And this is something you experience every day when you're riding the elevator. You feel that little bit of push down as your body adjusts to that larger acceleration. All right, question number 34. At the bottom of a hill, a car has an initial velocity of plus 16 meters per second. So you can say V initial equals plus 16 meters per second. The car is uniformly accelerated, so A equals negative 2.2 meters per second squared for 5 seconds. So the amount of time is 5 seconds. As it moves up the hill, how far does the car travel during this 5 second interval? So here I've got my givens, here I've got my unknown, and for my equation, I'm going to take a look at page 6 on the reference table. That's all of my mechanics stuff. And I see I have an equation, the fourth one down, that tells me that the amount of distance I travel equals my initial speed multiplied by how much time plus 1/2 times the acceleration times the amount of time squared. And so I can go ahead and plug in my numbers, being very mindful of the positive and negative signs. So I have 16 times 5 plus 1/2 times 2.2 times 5 squared. Again, that acceleration is negative. And so one thing I know, if I do 16 times 5 and get 80, right, I expect that my answer's got to be less than 80 because I'm subtracting something off of it. So I can eliminate answer choice 1. This one, I will then do my plus 0.5 times negative 2.2 times 5 squared. And I get as my answer 52.5. All right, answer choice question 35. A particle enters the electric field between two oppositely charged parallel plates as represented in the diagram below. Which particle will be deflected towards the positive plate as it enters the electric field? So let's just sort of sketch in, the electric field here, just to remind us of what's going on. We know to be deflected towards the positive plate, you need to have a negative charge, right? So negative charges would go up, and positive charges would go down. And we're just going to run through the list here. Photons, no charge. Neutrals would go straight through. So photon wouldn't go through, and neutrino wouldn't go through. They are both neutral. They would not deflect, they'd go straight through. And then let's see, we're saying negatives go up towards the positive plate, and protons would go away, or positives would go away. So proton is out, and electron is our answer choice. All right, question 36. As represented in the diagram below, an object of mass m located on the surface of the moon is attracted to the moon with a gravitational force F. An object of mass 2m at an altitude equal to the moon's radius above the surface of the moon is attracted to the moon with a gravitational force of. And so in order to talk about gravity at this type of scale, we would use Newton's universal law of gravitation, which states that it is equal to big G times m1 times m2 over r squared. And so to solve this question, we're just going to use some proportional reasoning. And so what this tells us is, let's see, we are doubling one of the masses, and we are doubling doubling the radius. The key here being that because it is the radius squared, we have to sort of square that doubling. So I get 2 over 4 equals 1/2, which means we're getting 1/2 of the force that we started with. Answer choice 3. I think the key here, at the very least, is to identify that because we are moving further away, that is the more important thing here. And so we would not expect the force to get bigger or for the force to stay the same. Now, it's possible if we change the mass by enough, it could happen. But generally speaking, something that if you're guessing at a question like this, you want to remember that the force of gravity, as you increase the distance, decreases. All right, question 37. The graph below represents the relationship between velocity and time for an object moving in a straight line. What is the magnitude of the object's acceleration? Well, if we look at our reference table, we're reminded that the object's acceleration is equal to its change in velocity divided by the change in time over which that velocity change takes place, which in the case of a graph means you're calculating the slope. calculating the slope is rise over run. You could pick any 2 points that you want. Why not make it easier on ourselves, and let's pick at 1 second and 2 seconds. So the rise here would be 10 meters per second. The run is 1 second. So 10 meters per second divided by 1 second is 10 meters per second squared. Of course, since this is a straight line, you could pick any 2 points, and you should get the exact same answer because the acceleration here is a constant. All right, question 38. 2 muons would have a combined charge of, and so the first thing we want to do is we want to look in the reference table because we're talking about modern physics stuff. We're going to the bottom of page 3, and a muon has a charge of -1 elementary charge. So the first thing we can do is we can eliminate answer choice 3 and answer choice 4. Eliminate answer choice 4 because that's a positive amount of charge, which isn't the case. And clearly we can't add together -1 charge and -1 charge and get 0. So what we are looking for, because there are 2 of them, we could kind of use process of elimination here and say the answer is going to be 1. But we might want to write down from our reference table how much an elementary charge is. 1 elementary charge is 1.6 times 10 to the -19 coulombs. So if we had 2 of them, that would be 3.2 times 10 to the -19 coulombs. But remember, we're talking about something that is negative. The answer choice is 1. Little behind the scenes sort of test design, you can see how these 2 answers sort of go together as a way to, as a distractor strategy by the test creators. And so looking at this question, you can maybe make a guess that it's one of these 2, 1 or 4, and therefore, as long as you can identify the charge as negative, you don't even necessarily have to do any sort of calculation at all. All right, next up, question number 39. 39 was a long one to read, and does involve some slight calculations here. So it was a little bit of a tricky one. All right, so 1.47 Newton baseball, or baseball, is dropped from a height of 10 meters and falls through the air to the ground. The kinetic energy of the ball is 12 joules at the instant before the ball strikes the ground. The maximum amount of mechanical energy converted to internal energy during the fall is. So we start off with some amount of potential energy because the baseball is 10 meters above the ground. Remember, to calculate a change in potential energy, we do mg times the change in height. Well, mg is the weight of the object, so we've got 1.47 newtons times our 10 meter change in height, which means our change in potential is 14.7 joules. Now, if there was no energy lost during the fall, then the final kinetic energy should be 14.7 joules, but it isn't. It's only 12 joules. And so where did that energy go? It went into the internal energy of the baseball as it fell, which is most likely heating up the ball. However, other things might be like creating sound or heating up the environment. So the answer to 39 is 2.7. 14.7 joules minus 12 joules gives us the 2.7 joules. All right, question 40. A projectile lands at the same height from which it was launched. Which initial velocity will result in the greatest horizontal displacement of the projectile? So we're going for horizontal displacement. Now, this was not a topic that we spent a lot of time in class on, although you did see it on some of the check for your understandings. So if we're talking about a projectile being launched, right, we might have a trajectory, right, a path that might look like this, or you might have one that looks like this, right? and one that looks like this. So it turns out at a specific speed, the greatest horizontal displacement comes when the angle is 45 degrees. If you're at an angle less than that, so let's say you're at an angle of, let's say, 30 degrees, that would be this angle here, you will not go as high. Compared to an angle like, let's say, 60 degrees, these, because they add up to 90, end up having the same displacement. It's just one takes longer to get there, right? So the one that goes higher up in the air spends more time in the air, yet doesn't go as far, right? And so as you go to angles closer and closer to 45, you sort of stretch out this path until eventually you get to 45 degrees, which would be the furthest horizontal displacement. So answering this question is a little bit tricky because you have to think about how you want to approach eliminating things. So the first thing I would say is my eye is going to be drawn to the highest velocity first. And so I'm comparing 3 and 4 first. And I'm saying, well, 3 is an angle of 45, so it's got to go farther than the 60 would. So I'm not yet saying 3 is my answer, but I can say if I was just comparing 3 and 4, it must be that 4 is further. I'm sorry, that 3 would have a greater horizontal displacement than 4 would. Then all I'm doing to check is to make sure that the other angle, or that the other example of a 45 degree angle, that its speed is less. So like 1 and 2 I can compare, and I can get rid of 2, right? Because 1 would go farther than 2, and now I'm left comparing just the differences in speeds between 1 and 3. And so I expect, and in fact, there's a formula that shows that you would actually go 4 times further in 3 than you would in example 1. And the reason for that being you are both going to go, you're going to go twice as high. And because you're going twice as high, you're going for double the time, and you're going at double the horizontal speed. So you're getting like a 2 times 2 effect there. All right, question 41. A 5 kilogram box is sliding across a level floor. The box is acted upon by a force of 27 newtons east. So we are applying a force of 27 newtons east and a frictional force of 17 newtons west. They're kind of nice here. They're not even telling you that that you have to remember that the frictional force is in the opposite direction of the speed. They're just telling it to you. If we want to figure out the magnitude of the acceleration of the box, we're going to use Newton's second law. This says the sum of the forces divided by the mass. Because our forces are in opposite directions, we have to subtract them. So we'll write 27 newtons minus 17 newtons, right, which is going to give us a net force of plus 10 newtons, meaning to the east. We're then going to take the 10 newtons and divide it by our 5 kilograms, and we're going to get 2.0 times 2.0 meters per second squared. Answer choice 2. Again, the equations for that is on page 6 of the reference table. All right, question 42. The diagram below represents a 2 kilogram toy car moving at a constant speed of 3 meters per second counterclockwise at a radius of 2 meters. Okay. The way I want to approach this is, I think what I want to do first is identify the direction. So the centripetal force is parallel to the centripetal acceleration. It always points towards the center of the circle. So if our toy car is located on the right side here, traveling north, then the centripetal force and acceleration pointing towards the center are pointing west. So let's go ahead and cross out choice 1 and cross out choice 3. Now to figure out the centripetal force, we do the mass of the object times the centripetal acceleration. Well, that would be the mass times v squared over r. So I've got 2 kilograms times 3 meters per second squared divided by 2 meters. So the 2 and the 2 here simplify to 1, and my answer is 3 squared. And so the answer is answer choice 4. Answer choice 2 is the number if you were just figuring out the centripetal acceleration. That would be 3 squared divided by 2, which would be the 4.5. But because they're asking for centripetal force, we have to also include the multiplying by the 2 kilograms of the toy car. All right, question 43. In which electric circuit would the voltmeter read 10 volts? Again, this one's a little bit tricky, and I think a good approach is to just go situation by situation, write down what the potential would be, and then once you find one that is 10 volts, then you are good to go. So in this first example, remember what a voltmeter is doing is it's comparing what is the potential on this side to what is the potential on this side. Now the potential across a battery or across a wire is whatever it's attached to. So one end over here is at 0, and the other end is 20, and so the difference there would be 20 volts. That is what the voltmeter in situation 1 would read. Very similar as you see in situation 2. The resistors are connected differently. This one is in parallel, and this one is in series, but the potential difference would be the same. In option 3, what we see here is we are measuring the potential across just one of the resistors. If our voltmeter was connected as so, then we would find that the potential difference would be 10, but because it's only over one of the resistors, this potential difference would be 5 volts. And so that is not our answer choice. So not 1, not 2, not 3. We're left with 4, but let's verify it. You can see in 4, it's this scenario I was just describing where we're sort of connected at either end of the 10 volt source. All right, question 44. The lambda baryon has a quark composition of up-down strange. Which particle has the same electric charge as the lambda baryon? So the first thing we've got to do is use our reference table on the bottom of page 3 to write down the charge of an up-down strange. So up is plus 2/3, down is minus 1/3, and strange is minus 1/3. 2/3 minus 1/3 minus 1/3 is 0. So we're looking for a particle that is neutral, that has no charge. Well, a neutron is neutral. It would have no charge. But we can run through these. An electron would be -1, a proton would be +1, and an anti-muon has the opposite charge of a muon. So a muon is -1, so an anti-muon would be +1. All right, question 45. How many kilograms of matter would have to be converted into energy to produce 24 megajoules of energy? All right, so this one's going to require us to do two things. First, we're going to have to get rid of the mega. So if I look at the prefixes for power of 10 on the first page, I see that mega is times 10 to the 6. So my energy is going to be 24 times 10 to the 6 joules. Because we're talking about converting matter into energy, we're going to use Einstein's equation, E equals mc squared. And if I solve it for the mass, I get the energy divided by c squared. Remember, c here is 3 times 10 to the 8 meters per second, which means c squared is 9 times 10 to the 16 joules per kilogram. So I'm going to do 24 times 10 to the 6 joules divided by 9 times 10 to the 16 joules per kilogram. So if I go and I put that in my calculator, first if I do the 24 divided by 9, I'm going to get 2.66. right? And then I've got to do like 10 to the 6 divided by 10 to the 16. Well, that's 10 to the 6 minus 16, which is 10 to the negative 10. So my answer is answer choice 2, 2.67 times 10 to the negative 10 kilograms. All right, question 46. A red photon in the bright line spectrum of hydrogen gas has an energy of 3.02 times 10 to the negative 19 joules. What energy level transition does an electron in a hydrogen atom undergo to produce this photon? Before we can use the chart on page 3 of the reference table, because that chart is in electron volts, we have to take our 3.02 times 10 to the negative 19, 19 joules, and convert it into electron volts. Well, to do that, we're going to sort of multiply by the fact that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. In essence, we're going to divide. So when I do that, when I do my 3.02 divided by 1.6, I'm going to get 1.8875, which, and then the 10 to the negative 19s simplified to 1, and so this is the amount of energy that I'm looking at. Because we're talking about this chart here, we actually sort of end up rounding this 1.8875. And so what I'm going to do is I notice that all of the transitions they have are ending at 2. So the transition at 2 has an amount of energy of negative 3.40 electron volts. And if I'm emitting light, then I must be coming from a higher energy level. Remember, higher here means closer to 0. So I'm going to add to this my 1.8875 electron volts. And what I find is, so again, I'm doing negative 3.4 plus that amount of energy, and I'm getting that wherever I'm coming from has an energy of negative 1.51 electron volts. And I look at my diagram, and I see that that corresponds to the n equals 3 energy level. And so it is answer choice 1. All right, question number 47. In the diagram below, a negatively charged rod is placed between but does not touch identical small metal spheres, R and S, hanging from insulating threads. What can be concluded if the rod repels sphere R but attracts sphere S? So the first thing we want to remember is in order for charges to repel, they must be like charges. So we can conclude that R must be negatively charged. So I can eliminate answer choice 3, and I can eliminate answer choice 4. To attract, however, something can either be neutral, and you would attract through polarization, or you could be oppositely charged, which means that sphere S, it doesn't have to be positive. It may be positive or it may be neutral. And so question 47, the answer is 2. All right, question 48. The amount of electrical energy consumed by a 60-watt light bulb in 1 minute could lift a 10-newton object to a maximum vertical height of. And so what we're doing is we're comparing the electrical energy, which is going to be based off of our power, so 60 watts times 1 minute. That's going to equal sort of the change in potential, gravitational potential energy, which is going to be mg times that height that we're looking for. We have to change the 1 minute over into seconds. So 1 minute is 60 seconds. And my mg here is a 10 Newton object, so I can just plug in my 10 newtons there. And again, I'm solving for that height. So I've got 60 times 60, which would be 0.3600 joules equals 10 newtons times that change in height. Divide both sides by 10 newtons, and I'm getting 360 meters as the change in height. Answer choice 3. All right. Question number 49. Microwaves can have a wavelength closest to. So in order to answer this question, we have to get an idea of what a typical microwave wavelength would be. So I'm going to page 2 of the reference table, looking at the electromagnetic spectrum, and I see that microwaves range from 10 to the negative 4 meters up to 10 to the 0 meters. Well, 10 to the 0 meters is 1 meter. That's like the size of a person-ish. Person's like 2 meters tall. And 10 to the negative 4 meters, that is a tenth of a millimeter, right? So again, what are we talking about? We're talking about things kind of like, a human hair-ish, okay? We're talking about things on the scale of like a person, right? So things like the radius of the Earth, that's way too long. Things like the height of Mount Everest, that's way too tall. Even something like the length of a football field, that's like if you figure that a person is, again, roughly 2 yards, like you're talking about 50 people head to head for the length of a football field. But something like the length of a physics student's thumb, right? Your thumb, the length of your thumb is maybe 3 to 4 centimeters, right? Which would be like 10 to the negative 2 meters. So it's falling right in the middle of that range. These types of questions are really tricky. And I think the way you have to work through them is by trying to write down sort of these powers of 10 to help you. All right, and then finally, question number 50. 2 pulses approach each other in a uniform medium as represented in the diagram below. Which diagram best represents the superposition of the 2 pulses when the pulses overlap? So I think the key to answering this question is to draw them actually overlapped on each other. So this is the pulse that's traveling from left to right, and this would be the pulse that's traveling from right to left. So I think one of the things to notice is that at the endpoints, right, we're ending up with a wave that starts, 0 plus something downwards, right? So we should end up with something that is below that horizontal. Okay, which means we can eliminate 2 and 3. Right? Because we have 0 plus a negative. So that corner should end up below. And sort of by symmetry, we've got our 0 plus something above. So we should end up with something that is above. Well, we've already eliminated answer choice 3, and now answer choice 4 isn't meeting that criteria. And so our answer choice here is 1. For a little bit of a sanity check, we should expect at this sort of spot of symmetry in the middle here, should be just as much right in the middle above as it is below, so we should sort of cross through 0 here. That's a feature that's also missing in answer choice 3 and answer choice 4, but is present in answer choice 2. All right, and so that is a step-by-step guide through the 50 questions of the June 2019 Physics Regents.